Okay. So another topic that we saw just yesterday is constrained partial derivatives. And I guess I have to re-explain a little bit because my guess is that things were not extremely clear at the end of class yesterday. So now we're in the same situation. We have a function, let's say, f of x, y, z, where the variables x, y, and z are not independent, but are constrained by some relation of this form. So some quantity involving x, y, and z is equal to maybe 0 or some other constant. And then what we want to know is what is the rate of change of f with respect to one of the variables, say x or y or z, when I keep the others constant. Well, I can't keep all the others constant because that wouldn't be compatible with this condition. I mean, that would be the usual or so-called formal partial derivative of f ignoring the constraint. To take this into account means that if we vary one variable while keeping another one fixed, then the third one, since it depends on them, must also change somehow. And we must take that into account. So let's say, for example, we want to find, because I'm going to do a different example from yesterday, so that if you really didn't like that one, you don't have to see it again. So let's say that we want to find the partial derivative of f with respect to z, keeping y constant. So what does that mean? That means y is constant, z varies, and x somehow is mysteriously a function of y and z through this equation. And then, of course, because it depends on y, that means x will vary. Sorry, x depends on y and z varies. So now we're asking ourselves, what's the rate of change of f with respect to z in this situation? And so we have two methods to do that. So let me start with the one with differentials, which hopefully you kind of understood yesterday, but if not, here's the second chance. So using differentials means that we'll try to express df in terms of dz in this particular situation. Okay? So what do we know about df in general? Well, we know that df is f sub x dx plus f sub y dy plus partial f partial z dz. That's the general statement. But of course, we're in a special case. We're in a special case where first y is constant. Y is constant means that we can set dy to be 0. Okay? So this goes away and becomes 0. The second thing is actually we don't care about x. We'd like to get rid of x because it's this dependent variable. What we really want to do is express df only in terms of dz. So what we need is to relate dx with dz. Well, to do that, we need to look at how the variables are related. So we need to look at the constraint g. Well, how do we do that? We look at the differential of g. Okay, so dg is g sub x dx plus g sub y dy plus g sub z dz, and that's 0 because we're setting g to always stay constant. So g doesn't change. If g doesn't change, then we have a relation between dx, dy, and dz. Well, in fact, we said we are going to look only at the case where y is constant. So y doesn't change. This becomes 0. Well, now we have our relation between dx and dz. We know how x depends on z. And when we know how x depends on z, we can plug that into here and get how f depends on z. Okay, let's do that. Oh. Uh-oh. Okay. So again, saying that g cannot change and keeping y constant tells us gx dx plus gz dz is 0, and we'd like to solve for dx in terms of dz. That tells us dx should be minus gz dz divided by gx. Okay, so if you want, this is the rate of change of x with respect to z when we keep y constant. In our terminology, this is partial z, no, this is partial x over partial z with y held constant. Okay, this is the rate of change of x with respect to z. So now when we know that, we are going to plug that into this equation. And that will tell us that df is f sub x times dx. Well, what is dx? Dx is now minus gz over gx dz plus fz dz. So that will be minus fx gz over gx plus fz times dz. And so this coefficient here